afternoon. Welcome back to Statistics for Business Research. This afternoon, we are going to look at linear regression models, a continuation of the correlation coefficient that we started from the first video. And our intention is to look at how to analyze models that involve relationship building. And regression models, and we are going to look at them this afternoon, will involve only simple linear regressions. Now, many statistical indices summarizes information about a particular phenomena under study. And as indicated earlier, Pearson summarizes the magnitude of a linear relationship between pairs of variables, and it also indicates the direction of the association. However, some scientific research objectives require that we explain, predict, and control phenomena. In that case, correlation cannot do that. So, to explain, predict, and control phenomena, we must not view variables in isolation. And that will mean that we need to look at models that can explain, predict, and control. And doing that will enhance our decision making because it provides a valuable clue as to how the variables relate. And the examination of this relationship leads to the formation of a network of variables that provide the basis for the development of theories about a phenomenon. And we are going to employ linear regression analysis. And linear regression analysis are statistical procedure which allows us to move from a descriptive to explanatory, prediction, and possibly control. And indeed, we are going to first look at the bivariate regression analysis. Especially that one is the simplest linear regression procedure. And we call it a simple linear regression because the model explores the predictive or explanatory relationship for only two variables and examine only linear association. So, for example, if we are thinking about looking at the relationship between y and x, this is a typical example of bivariate because it involves only two variables, that is y and x. If you are looking at w and z, so interest rate and say inflation, then in that case we are looking at bivariate. Simple regression focuses on explaining and predicting one of the variables on the basis of information on the other, as we have indicated. And the model thus examines changes in one variable as a function of change or differences in the value of the other. So, for example, if we have y and then we have an x, then we are looking at how changes in x influence changes in y. So normally, and in that case, we will call the y the dependent variable and we call the x the independent variable. So the regression model labels variables according to their role. We have dependent variable, that's a variable whose variation we want to explain or predict. So if you want to predict y becomes the dependent variable. And the independent variable, the variable used to predict systematic change in the dependent variable. So we are looking at if s changes, what will happen to y? So x is now dictating the pace of where y should be. So x is being used to predict y. In that case, x becomes the independent and y becomes dependent because y depends on x. Mathematically, we can write the regression equation as y equals a plus bx plus e, where y is the dependent variable, a is the constant, b is the coefficient of x, which is measuring the sensitivity of y to x. So it's looking at if s changes, why something should happen to y by what magnitude. B will tell us that magnitude, and E is the error term. So we are saying that S represents the scores for individuals on the criterion and predictor variable respectively. So X is now going to predict Y, and the parameter A and B are constant describing the functional relationship in the population, and the value of B identify the changes along the Y scale expected for every unit change in a fixed value of X. So normally we say it represents the slope of or degree of steepness. The value of A identify the adjustment constant due to scale differences in measuring X and Y. So the intercept or the place on the y-axis through which the straight line passes, and its value is the value of y when s is equal to 0. So that is the constant, and y is measuring most of the other determinants that we were unable to account for. There are some of them because the variation of y, we are saying that is based on x, but it's not all the variation in y that will be dictated by x. There are some unknown, and that one is being captured by the error term. So as the error term becomes bigger, then it means that there's something wrong with our model. And before you can run a regression model, there are some assumptions that you need to look at. So let me say assumptions. So these assumptions, one, they are similar to what we looked at from the other parametric tests, but with some addition. One, the dependent variable should be measured on a continuous scale, and we say that it should be either interval or ratio levels data, that is numeric. In some cases, you can also have ordinal continuous, but the independent variable can be measured on ordinal, continuous, or nominal. So it means that though we are talking about numeric, we are talking about interval or ratio, the dependent variable is of our interest. The dependent variable should be measured on interval or ratio, but the independent variables, the s, could be nominal, could be ordinal, and could be continuous. Then we also need to ensure that samples of subjects should be randomly sampled from the population of interest. So we need a random sampling from the population. Then we also ensure that the scores for the dependent variable is normally distributed, and we can check that one by inspecting the histogram of scores, or we can also use other statistical tests for testing normality. But as we have indicated earlier, if the sample size is large, we can ignore the issue of normality, or because the departure from normality will not seriously affect the result. Then our sample size, the next one is that our sample size should be large, and that is where sample size is large, because basically if you are want to run regression, we expect that the sample size divided by n, where n which is the number of, divided by the number of independent variables. Independent variables should be greater than 15. Okay, so if your sample size is n, then you have n divided by independent variables iv should be greater than 15, or 12 with caution, meaning that we expect it to be greater than 15, but if it's greater than 12, it's somehow okay. But we have to be mindful of the results when we are interpreting the results. So this is one option of looking at it. Or roughly, we can also say that our sample size, our n, should be equal to 50 plus 8 times IV, 8 times number of independent variables. Okay, so it means that if your sample size is is 50, or if you have 5 independent variables, for example, if you have equation of y equals a plus b1 x1, sorry, let me delete this once. Y equals a plus b1 x1 plus b2 x2 plus b3 x3 plus b4 x4 plus e. This is a multiple regression. Okay, this one, the number of independent variables. The independent variables are x1, x2, x3, and x4. So it means that you have 4 independent variables. You have 4 independent variables. Then your minimum sample size required when analyzing these data should be equal to n equals 50 plus 8 times 4, and that will give us this 32 plus 50, that will give us 82. Okay, or you can also use this alternative, the second alternative, which says that when you divide the sample size by n, you should get 15. In fact, the two options, the one that will give you larger sample size is better, because there's always a saying that more information, more data, more information. So you always want large sample size. So you can also try that n should be greater than 15 times the number of independent variables, which is 4, and that should say that your n should be greater than 60. Okay, but between the two, the one that will give you the larger sample size is required. So in this case, we prefer using 82. So 82, minimum of 82 is required. That does not mean that the sample size should be 82. So for example, if you have 1,000 and your sample size is maybe 384, maybe 300. So if your sample size is 300 for 1,000, using the sample size determination formula or sample size determination table, then we expect that the number of variables that enter into the equation will satisfy this function. So if you have 1,000, it means that anytime you divide 300 divided by the number of independent variables, it should be greater than IVs, it should be greater than 15. Meaning your 300 should be greater than 15 times the number of independent variables. Okay, so you can do that and then get about, divided by 300, 15 divided by 300, what do you get? Yes, that will give me 20. Okay, very good. So 20 IV, it means that your independent variables cannot be more than 20, because when you get more than 20 independent variables, you will not satisfy this assumption. So when you want to see whether your sample size is large, these are the two indicators that you use. Either you use this one or you use this one. Okay, thank you. The next one is to look at the linearity between the variables. So you have to make sure that there is a linear association between the variables involved. So before you run the regression, you need to check correlation between this and that, between this and that, between x and y. Then you also need to check between x4 and y. So you check correlation between xy and y1, s2 and y, s3 and y, s4 and y, and make sure that there is a significant correlation. If there is no significant correlation, the implication is that there wouldn't be any relationship between the variables involved. So there should be a significant correlation between x1 and y, x2 and y, s3 and y, s4 and y before they can be entered into the equation. So those are the issues of linear association. Then the next one is to check for multicollinearity. Check for multicollinearity to avoid redundancy. Normally, I always use the example that coaches avoid fielding more 3 or 4 strikers in a match because some of them will be redundant. So if you want them to be effective, we don't field more than 2. You don't field more than 2 strikers in a match, but rather you field 1 and the others will provide support. So you need to check whether there's no multicollinearity. So you check the correlation between this and that, this and that, this and that, then this and that, this and that, then this and that. So you check the correlation among the independent variables and make sure that the correlation among the independent variables is not more than 0.9. So if there's a correlation of 0.9 between any of the independent variables, that variable should be dropped. So for example, if I see that there is a correlation between this and this is 0.9, it means that they are highly correlated and possibly one of them should be used and one should be dropped. So between S1 and S2, I have to check and see if the correlation coefficient is not more than 0.9. Then you check between S1 and S2 and see if the correlation coefficient is not more than 0.9. Then X1 and X4, then make sure that it's not up to 0.9. Then you also check between S2 and S3, S2 and S4, and then S3 and S2. Once they are more than 0.9, it's an indication that we are going to get multicollinearity. Well, assuming that you allow that one to stay, then after the regression, you need to also check the variance inflation factor. And if there's a multicollinearity, we can also see from the variance inflation factor. And if the variance inflation factor is above 10, it is a cause for concern. We should be concerned for that. So, and if it is less than 10, it means that there's no multicollinearity. And don't forget that the variance inflation factor moves with what we call tolerance. And for the two, tolerance is equal to 1 over variance inflation factor. So we expect our variance inflation factor to be less than 10. So if the variance inflation factor is less than 10, it means that there's no multicollinearity, and that is what we want, no multicollinearity. That is right. If we have variance inflation factor greater than 10, then it means that there's problem with our model. If we are also using tolerance as an indicator, then we want our tolerance values. These values will be computed alongside your regression when you are using any of the Sascar software. So if the tolerance is